So we have a linked list that we'll see in class. And for the lecture question, we're going to add one method to this. So we want to add the append method to the linked list node that's in the examples repo. Go into the examples repo, week 11 linked list node. That's the class you want. Just leave it in the week 11 package or copy it into a new project, but make sure it's in the week 11 package linked list node and keep all the functionality that's there, except add the append method to it. And we're going to talk about append a bit and see why append is actually something that we don't really want to do with linked lists. It's a pretty expensive operation. It's an OFN, a linear runtime operation. So it's pretty slow, and you're going to see that in the lecture question. You have to do a decent amount of work to actually append to a linked list. So let's talk about linked lists and how they're built. So first, just a little flashback, 2 slides on arrays. Arrays, way back in week 2, we did a comparison to arrays and lists. An array is a sequential data structure. It's one continuous block of memory. So when we create an array, we're asking for one block of memory that's all sequential, and then we use the indices of the memory addresses themselves to be able to access information. This allows us to access information very quickly. It's an addition and a multiplication to find the index that we're looking for. Given the first index of the first element of the array, which is the only thing that's stored when we store an array, do just a little bit of algebra to find any element in that array with O of 1 lookup. So it's constant time lookup. It's 2 operations, 2 is a constant. Doesn't matter how large the array is, we can find the memory address we're looking for in constant time. This gives us something called random access, when we can access any element in constant time. We have random access. That's what we get with arrays. Problem is, they're fixed size. Once you say, hey, operating system, give me this chunk of memory that's this big, as soon as we create that array, some other parts of our program or other programs might take up the memory addresses right after our array. So if we want to add another element to this array, we can't do that in the general case because we don't know if we have access to that next memory slot or not. So in general, we just can't do that. If we want to add to an array and resize it, we have to create a whole new array, ask the operating system for a chunk of memory equal to the size of the new array, the new one that we want, copy over all of the elements, and then destroy our old array. Now, a lot of languages will do this for us, but this is what's happening under the hood. A JavaScript array list, a JavaScript array, a Python list, they're all going to do this resizing for us. They're going to have some underlying array in that data structure, and as you start adding elements, whenever it needs to resize, it does that resizing for us, which is a pretty expensive operation. But if it doesn't have to be done too often, we can actually mitigate the cost of that. But that is a fact that we have to deal with when we're working with arrays. We have this chunk of memory. We don't have access to the next memory spot in general, so we're just not allowed to use it. And then we use the starting memory address and then the size of each element and the element index number to figure out the memory address of that value, of the next value. So that was a quick review. Let's talk about what we've talked about with linked lists way back in week 2 also, but we'll obviously spend more time on the linked list implementation. So this is also a sequential data structure. All the elements have a fixed order. This is opposed to something like maps in Scala, dictionaries in Python, objects in JavaScript, and maps. I think they just call them maps in Java. These do have an ordering where those data structures are just listed, do not have any specific ordering. When it's a key value pair, there's no meaningful ordering to those values, to those. But these are sequential. Linked lists do have a fixed order. There is some meaningful notion of order in these lists. But these are variable size in that and the way we get variable size is instead of asking for one big chunk of memory and storing our whole linked list in that chunk of memory, what we're doing now is asking for a new chunk of memory for each element of our linked list. So every time we add a new element to our linked list, we're asking our operating system for a new chunk of memory that has enough space to fit that one element and a reference to the next element in the linked list. So just enough space to hold those two values, and we don't care at all where in memory that is. We don't care where that is. We're just going to have each node remember its value and where the next node can be found. So a linked list, instead of being just one fixed data structure, one block of chunk of memory, instead we're going to build a linked list based on linked list nodes. Each node is going to store one value and a reference to the next node, and then we can traverse through the nodes to see all the data of the linked list. So here, if we have a linked list at 506, and we only store, we'll only store the reference, just like the array of reference, that memory address of the first element in the linked list. We're going to store this as our list. So the list is only a reference to the first node. We're going to look at that node. It has its value, the first value in the linked list, and a reference to the next value. If we follow this reference, we can find the next value of 3, and also a reference to the next value in the next node in the list. We can follow that, find the next value, and then as soon as the next node is null, then we know we've reached the end of the list. And there are different ways to represent the end of the list. We're going to have the next value be null. There are other ways to do this, but this is one of the simplest ways to visualize, so we'll stick with this one. So this list is the list containing 531, and note that we don't care where each value is in memory. Every time we want to add a new element to this list, we're just going to ask our operating system for more heap space, get the reference to that heap space, add the value, add the next pointer, and then take that reference and set it as the next value of one of our nodes. So these nodes are linked together in memory in some way just by the references, but they're not actually associated in memory outside of just having these next values pointing to the next node in the list. So right there is most of what you need to know about linked lists. The rest of the time we're just going to talk about implications of this. Okay, we have this data structure that's spread out throughout memory. What does this mean? Why do we care? And how do we work with this? How do we work with this data structure? But this is the main idea of what we're doing. Let's look at it the very simplified, I just took all the methods out of that linked list node class. Let's look at the code. The simplest code that can represent this is we have a linked list node with its value and also a pointer to the next node in the list. These are the two values we need. No functionality yet. We'll look at the functionality. When we create one of these, we want to create a list that just stores the value 1 and null, so we'll create this node first. We want to create this node. We'll give it the value 3 and a reference to that node that was created. And when I create this next node, so right now this is going to return, in our example, the memory address 795. We're going to overwrite my list with that 795. So instead of my list storing 416, it's going to store 795 right now. So now when we create the next node, which will be the first node of our list, we'll create a new node, give it 5, give it 795, and then this is going to return 506, which is the ultimate value that we're going to store in our linked list node, which will represent our entire linked list. This is what we're doing when we call prepend on a linked list. Whenever we call that operation, and any operation on our lists in Scala, we always reassign the list back to the original variable. This is why we're doing that. This list holds a reference to a certain node in this linked list, and we're going to overwrite that with the new node, but we still maintain the information of the old node. We still have the rest of the list there, but we're going to return a new reference and keep reassigning that reference. So this code here builds this linked list here. Oh, and yeah, nomenclature there. The node, the reference to the first node in the linked list, we call that the head of the linked list. And in Scala with the list, if you want to get the first element, you can do mylist.head. That'll give you the first element in the linked list. So that's where that nomenclature comes from. The head is the first node in the linked list. All right, any questions on the structure of a linked list node before we go any further? Yeah.
A couple of questions, but they go hand in hand. One, how come it's a linked list node with generic type A? Because couldn't you just use var value of type any? If you kind of what I'm saying?
No, I do get what you're saying, but so that would be like creating if you have a regular Scala list, and you say, give me a list of any, it would be the same thing as doing that. So if you want to create a data structure and store any different type, if you do any, you can do that, but you're not going to have necessarily the functionality that you need without doing a lot of type casting. So whenever you access an element from a list of type any, you got to cast that to the type that you want. And if that element actually isn't the type that you want, you're going to get a runtime error. If we use generics like this, if we use that type A, when we create a list, we say, this is going to be a list storing this type. And now our compiler is going to check all our types throughout our program and make sure that we don't have those pretty dangerous typecasting operations. This typecasting is going to lead to runtime errors when we make a mistake. If we use generic types like this, we're going to have compiler errors when we make a mistake, which are really easy to catch. Try to run the program, the compiler says no with a bunch of red text, and you know that you got to fix that before you ship to your clients, to your customers. Is there another question? I saw another hand. Yep.
So in order for us to use the list, we must create a class and then implement nodes?
Yeah. Yeah, so if we want to create a linked list, we'll create a class, some node class, and then work with them. And and I should give a warning that most of what we're going to see this week and next week with linked lists this week and trees next week, you wouldn't really do this. I'm just doing this to show you. I need to show you how a linked list works, how a tree works. But if you go into the actual list class in Scala, it will have nodes like this. It actually has different types of nodes, and the nodes have all these operations that we're working with. And then the list class just stores a reference to the head node. You know what? This is worth taking a quick look. Oh, don't do it to me. So the list class, look at all these mix-ins, ooh baby, only has a reference to the head of the list. Oh, it actually has a reference to the tail too. Like some new thing. But it has a reference to the head node of the list. But it doesn't have a reference to anything else. And the head node, which here looks like just the type, but we can do this. But the node class is actually named this : So syntax gets weird here, but this is actually the node class that we're working with in lecture. So whenever we have a linked list implementation, this is under the hood how it's going to be behaving. But we don't get to see the details when we're just using a list in Scala. We want to see, if you're going to be a computer scientist, we want to see how these things work. So you can understand the trade-offs when you use a list other than an array or a hash table. We want to see all those trade-offs, which you'll get a healthy dose of next semester in data structures. You'll see all kinds of different data structures. For now, we just want to get an exposure to a few different ones and kind of get a taste of it. But yeah, you would create a node. I got away from the original question again. But we'll create these node classes, and that's how we create these linked lists. One more side thing. If you are brave and going for the bonus in the homework, the nodes in a neural network, you can create those, each node as a class too. In my solution, I created 3 different classes: input nodes, output nodes, and hidden nodes, and then had them all linked together with lists of all their connections. So you can use this same structure and expand it to more complex structures as well. All right, so we have these lists that are nodes linked together by storing a reference to the next node in the list. So how do we work with this? There are a lot of things we would like to do with any data structure. I want to ask it for its size. I want to be able to know where a certain element is. I want to add elements. I want to remove elements. Find a specific value. I think I pushed that off till Wednesday. But we'll add and remove and do the rest of these. There's a bunch of things, just natural things that we want to do with our data structures. How do we do them with this structure? So let's take a look. And we're going to use lots of recursion. You can do some of these operations without recursion, but I wouldn't recommend it for the lecture questions. For today's lecture questions, I'd recommend that you do use recursion just to get used to using recursion. It's possible with linked lists. You can get away without using recursion. You can write this as a loop and say if next equals null. But next week when we get to trees, it's going to be much more difficult to pull off. So if you want to be ready for the trees, I recommend getting your practice with recursion. Well, the recursion is pretty straightforward at this point. So size, I'm going to write this as a recursive function. The size of a linked list starting with any node in the list. So I want to know if this node were the head node of the list, what's this list's size? Or in other words, from this node to the end of the list, how many elements are there? Well, if my next reference is null, there's nothing left. I'm just going to return 1. I'm going to say, hey, I know size 1. There's nothing after me. Just return that value. If next is not null, I have at least one more element. I have no idea how many more elements there are, but at least one more. So I'm going to recursively call size on the next element. And when it returns its size, I'm going to add 1 to it for me, for myself, and then return that value. And then if we call .size on the head node, it's going to return the full size of the list. Question?
Well, size is the same thing.
Yeah, so the question of .size is the same as .length. Yeah, in most cases they're interchangeable. It depends. I think most languages and libraries use both just because some use one, some use the other. Newer stuff just says, we'll use both, then there's no confusion. But yeah, they're pretty much interchangeable. Go.
What is plus 1 do? Is that next size plus 1? What is that?
So the +1, that's representing the element in this node that we're calling this on. So each node is going to say, ask the next node in the list. It's going to say, hey, what's your size? Because each node knows that its size is the size of the next node plus its element. So if somebody's asking me, hey, what's your size? I'm asking the next node, hey, what's your size? And when they tell me their size, I add 1 to that and then return that up the chain. And if everybody's doing this and the very last node says, I'm just size 1 because my next is null, it's going to say, hey, I'm size 1. The second to last node is going to say, oh, you're size 1? Well, I have 1 element too, so I'm size 2. The next one says, oh, you got 2 elements? Well, I got 1, so that's 3. And pass that up the chain. When that gets all the way up the chain, all the way up the recursion, the head node is going to add its 1 to n minus 1 and say, here's the size of this list. Any more questions about this one? This is probably our first practical use of recursion. So it's fine if we spend some time right here. ToString, very similar. If this is the last node in the list, so if next is null, just return its value .toString. Else, recursive call to ToString. Recursive call to ToString plus my values ToString with a comma in the middle. This is probably the next thing where we actually see, like size, we can imagine doing size as a loop, not that big of a deal. One nice thing that we finally get to see here, and we'll see very much so next week, Recursion is going to help us. This is the first time we see Recursion helping us in reducing our workload a little bit. If we use the loop here, we have to have some way of knowing not to put a comma either after the last element or before the first element. With Recursion, that's automatic. The last element is already being handled special, so the last element, we're just not adding a comma there. And for any other element, we're adding a comma in between the elements that we're adding. So we see a little bit less work. If we have a loop, we got to not only set up the loop, but also have a conditional inside the loop to say, is this the last element? If it's the last element, don't add a comma after, else add a comma after. Not much work, but hey, Recursion cuts a little bit down. Any little bit we can say we're happy about. Accessing an element by location. This is one we've used a lot throughout the semester. I used this in the slides quite a bit. We used it last week to make our sorting algorithms really inefficient, is apply. Give me the element at index I. It's not really an index because indices don't exist in a list, but give me the ith element in this list. We don't have random access like we do with an array. With an array, we just do a quick multiplication and a quick addition. We know exactly where in memory that ith element is, because it is indexed. Not true with a linked list. With a linked list, we have to traverse the entire list. We only have a reference to the head node, so we have to ask that head node for its next, that node for its next, that node for its next, and keep traversing this list until we reach the ith element. So we have a lot of work to do. This is a linear runtime algorithm just to access the ith element in a linked list. This is a very expensive operation for a linked list, and it's a very common application. So this is something, if we're not careful, like last week with our sorting methods, before we use that foreshadow, merge, and merge sort, if we're not careful and we're just using apply very liberally around our code, we're going to crush the runtime of our algorithms. If your algorithm is something that, say, generates a bunch of animals and has a whole bunch of generations, and you're using things like apply, you can see a pretty big hit in the runtime of your algorithm. And with the genetic algorithm, the algorithm has to be fairly efficient because it has to run a lot of those, running over and over for this guessing check. So being aware of the runtime of the methods that we're calling, especially if we're using linked lists, it's going to be important so we don't see a huge blow up in runtime. So how does apply work? Well, we have to navigate I times. If I is 0, we're just at the head node. So if I is 0, return myself. We're going to return that node. That's going to be the return value of this. We could change this to return the actual element, return an A, and do this dot value. That'd be fine too. The way I set it up is to get the node, so we can do inserts and deletes later on. So if I is 0, just return this. We've reached our destination. Else, tell the next node, apply I minus 1. So we have the minus 1 to say, look, we just took care of one step in this apply method. We took care of one step. Tell the next one to go one less than I. And then as I decreases, we're going to go that many steps. And then we'll reach 0 right at the right element, and then return that all the way up to recursion. Adding an element. So this starts, say we want to add an element in a particular place. This starts by finding the node where we want to add the element. So if we want to add an element somewhere in the middle of this list, so we want to add after 3 the value 2, we're going to have a reference to the node containing the value 3. Once we have that reference, this is easy enough. Once we have a reference to the node containing 3, we're going to change its next value to point to a new node that we created. And the next value, the old next value that was in that node, is going to be the next value of the new node that we created. So whatever this value was pointing to, this node here, the reference to this node, our new node has to point to that old reference, and then our node that we added to is going to point to the new node that we created. So we're manipulating a few pointers to be able to add an element, but we need a reference to that first node before we can add it. This is, aside from having to have a reference to that node, this is a huge advantage of linked lists in that we can add a node anywhere in the list if we have a reference already in constant time. All we did was update 2 pointers and create a new node. There's no mention of n, the number of elements in the list in there. It's all constant time operations. We have constant time insertion at any point in the list. Compare that to an array. For example, you have an array and you want to add a value to the front of an array. It is a very expensive operation. That's O of n because you have to move everything in the array down by 1 index. You actually move it in memory and then add your element to index 0. It's a very, very expensive operation to add to the first element of an array. Or any element, that's the worst case, but adding an element to an array is very expensive. Linked lists, no big deal at all. So if we want to insert some value, give it a reference, so we're calling insert on the node that we want to insert the new node after. We're going to call it on that node, on a reference to that node, the new element, create a new linked list with the old next, and update this values next. So we can get all that done in one line, updating the 2 references and creating a new linked list node. We can do this as a one-liner, but we have to have a reference to that node. So finding the reference could be expensive. That could be an O of n operation. If we want to find, say we're maintaining a sorted list, and we want to find the value in this sorted order. Where does it go in this sorted order? It's going to be a linear runtime operation to find the node, but then a constant time insert. Insert's really easy. Similar with delete. It's a very simple operation in terms of runtime. It's constant runtime if we have a reference to the node already. So if we have a reference to the node before the one that we want to delete, we have to have a reference to the node before the one we want to delete. So say I want to delete 2 from this list. I'm going to take the node before it and update its pointer, its next value, to the node that I want to delete's next value. So delete is as simple as that. Delete's easy. Now we actually didn't do anything to the node we're deleting, but since we no longer refer to it from anywhere, it's good as dead. It's gone. We can't access that element anymore. Its next still points to this linked list, but we have no way of getting to that node anymore. It might as well not exist. In fact, it's going to get garbage collected because nobody refers to it anymore. We no longer have a reference to it. So this is going to be gone on the next JVM garbage collection. It's gone. So all we had to do was update next to the next element after the one we want to delete from the node that's before the node we want to delete. We update 1 pointer and that's it. That node's deleted. In a language like C++, we'd worry about our memory leak there. Run it on the JVM, we're going to let the garbage collector take care of that. Yeah.
Does it still take up memory since it's not deleted?
It'll get deleted. So the JVM on the next garbage collection, we haven't talked about garbage collection much, but once you have an object on the heap that you no longer have any references to that object, it's gone. The next time the garbage collector runs in the JVM, it'll clean up all that heap space, because if we can't refer to it anymore, it knows we're done with it, because we'd have to just guess at the reference, we just have to search through memory. We're not gonna do anything like that. So that's when the garbage collector knows, okay, this is gone, they must be done with this, my programmer must be done with this, I'm gonna clean it up. So since this .next, the old one, we no longer have any references to that, unless somewhere else in our program we have a reference to it, then it'll stick around. But if this is the only place we were using that node, it's gonna be gone. Garbage collection is gonna take care of it, so we don't have a memory leak here. C++, if you're not using the new language features and you're not using any of the pseudo garbage collection, that will be a memory leak, and your programs are gonna start crashing, running on heap space. All right, back to the lecture question. So, I want to look at one of these. Let's go with apply. So here I have a linked list, and this is the output of this program right at the bottom. So here I'm creating a linked list. This is the one that we created in the slides. I'm going to create a node containing the value 1, using ints, the value 1, and null, so this is the tail of my linked list. I'm going to add 3 before the 1. I'm going to add 5 before the 1, so I'm prepending each time. So what I'm doing here is just writing a method that's going to do exactly that. I'm going to take the head of a linked list and add an element before the head. Now this is a very nice operation. I'm going to create a new linked list node with the new value and set next to this. I'm calling this prepend method on the head node. So this is a reference to the head node. If I want to add a value to the beginning of the list before the head, I'm going to have next be this, which is a reference to the head, and add that element to that node, and then return that new linked list node. So if I'm prepending, I take this list, 532, and I prepend 10 to it, and reassign that to my list. That's how I'm getting that next value at the beginning of the list. This is the same as saying great name there, but this is the same as saying this. So we're doing the same thing as the built-in list. We're just naming the method a little different, and we're not using this inline syntax. We're calling it like a regular method and prepending and then returning a reference to the new head node of the list. So I want to prepend 10, 11, and 12, and my new list is now 12, 11, and 10. So what I want to look at here is when we call apply of 4 on this list, I want to go into the debugger here. So I always mean to use the debugger a lot more in lecture. I strongly recommend all of you use the debugger. Whenever you're running up against something you don't understand why your program is behaving the way it is, you're failing your own tests or anything, run the debugger and just see what your program is doing. So when we first get to this point, we can see my list. It's calling my toString method and getting the list printed out in a nice way. And let me step through this a few times and see. Right now, I'm at the head node. The value is 12, and next, it's calling toString on next, but the next is at location 958 and has the remaining rest of the list. And I is 4 at this case. So since I is not 0, we're going to hit the else, and we're going to call apply on the next node in this linked list. When we call it on that next node, we're now at the node containing the list 11, 10, 5, 3, 1. So everything except the head node And each node behaves as its own complete list, its own complete linked list. Its next is 10.5.3.1. Its value is 11. I is 3 at this point. So we're going to call next.apply of 2 on the next list, that 10.5.3.1. I is 2. So we're going to call apply on the next list. I equals 1 on this list. We're going to call apply of 0 on the next list. So we're at that list that just contains 3 and 1. The value at this node is 3. I is 0. So now we're going to return this list itself, this linked list node. Or you can think of it as the list with this node as its head. So now we're going to return this. And you can see our recursion here, by the way. We have all these recursive calls on the stack that haven't resolved on each one of those nodes. So now we're going to return this, go back up the recursion, return this. This is just going to return the return value of this call. And eventually we get to the top level of the recursion. They actually did shortcut it because it's tail recursion there. But we're going to get back to the main method and actually get the final return value of that list. So we traversed down 4 nodes. That node returned itself, and then that return value went back up the recursion. So with that recursive call, we were able to get the correct reference node from that list. And when we step one more time, we'll get to see that 3. So we did in fact return 3 by accessing the value of that node. But we're returning a reference to the node. So say we wanted to add an element after that node, or we wanted to delete the element after that node, we have access to those methods as well, since we're returning the whole node instead of just the value at that node. All right, yeah, we're out of time. All right, with that, I'll see you on the stage.